Hi, my name is Phil, and I am a senior lecturer in astrophysics at the University of Lincoln. And welcome to this video. In this video, I want to kind of go back over again galaxies and actually go back to dwarf galaxies again and look at one of the more rarer types of dwarf galaxies that we have, which are blue compact dwarf galaxies. And these are kind of like an unusual type of galaxy, but they do share common properties with larger galaxies and other dwarf galaxies as well, but they obviously have some unique features, which is why they're called blue compact dwarf galaxies. So before we do that, let's have a recap of galaxies in general, and then a recap of dwarf galaxies, and then we'll go on to the compact blue dwarf galaxies. Now, if you've seen all the other videos, you could probably skip all of this and go straight to the bit that concerns the blue compact dwarf galaxies. But anyway, just to recap on your main galaxy types, you actually have this tuning fork diagram, which is used for the classification. There's a few variations on this, but quite commonly known as like the Hubble classification system, and it looks like a tuning fork. And on the right-hand side of that, you have spirals. These are disk-like galaxies that have spiral arms, hence their name. And depending on which diagram you actually look at, there might be 2 or 3 branches there. This one has 2. On the top, you've got your normal spirals, and on the bottom, you have your barred spirals. And interestingly, you have an intermediate one which goes in the middle sometimes as well. So they're kind of in between. They have a weak bar, but they basically sit on the right hand side of this, and they evolve from the right hand side to the left hand side. It basically means that their spiral arms get more tightly wound, they lose gas content, and then they transition across to the left. And it's the same, well, the same is true for the barred spirals, the normal spirals, and the intermediate spirals, although they can possibly change branches because some galaxies can actually evolve bars. But anyway, it's a whole different story. This is where they kind of sit. Now, some key features about spiral galaxies is they generally have high gas content. Now, as they age and evolve, that gas gets depleted because it's formed into new stars. Spiral galaxies will have a higher content of young blue stars. Younger spirals are going to have more, so they'll appear bluer. And they have disk-like dynamics, which basically means they have a fairly significant net rotation, a bit like a disk. So that's the key things really with spirals. There are obviously lots of other things going off there, but these are like the key things just to kind of recap you. And then the ellipticals, these sit on the left-hand side of this classification diagram, and they're typically just classified by shape, and they can be spherical, which would be an E0, or they can be more cigar shaped, which is E7. Now, it's possible that these E7 and the more cigar shaped ones are not true elliptical galaxies, they're actually kind of lenticulars that are angled. But again, completely different story for a different video, that one there. But they're basically classified by shape. And the key differences between elliptical galaxies and spirals, well, something I actually haven't put here is that they're featureless. And by featureless, I mean they don't have any large scale structure like spiral arms, bars, that sort of stuff. So they're quite smooth in appearance. They don't have any star formation. So they actually have a older population of red stars because they don't have those young blue stars because they've not undergone any recent star formation. And the reason for that is they just don't have any gas in. All of their gas has been depleted, so they don't have any means to then form new stars. And the movement of the stars is random. They don't have a net rotation. However, that's not necessarily true. Actually, quite a few elliptical galaxies do have a modest net rotation, but it's significantly less than spiral galaxies. So they do have less rotations, even if they are rotating, but quite often they'll have more randomized motions of the stars or velocity dispersion compared to a spiral galaxy, which will have a significant net rotation and a disk-like dynamics, basically. So, dwarf galaxies then. Dwarf galaxies are kind of like galaxies, but they're just smaller. And this is an example of dwarf galaxies in relation to our Milky Way. Now, our Milky Way might have a diameter on the order of 100,000 light years across. They can range, plus or minus that. Milky Way is a reasonably sized spiral galaxy, and then dwarf galaxies can be on the order of just a few thousand light years across to 10,000 light years. So You're talking like 10% and below the sort of size of the Milky Way. So they're quite small galaxies. And mass-wise, they obviously have significantly less mass in them. Dwarf galaxies can have billion times the mass of the Sun residing in them, whereas the Milky Way is on the order of trillions of times the mass of the Sun. Now, elliptical galaxies generally, that's where you're going to find your much larger or your biggest galaxies, but they also have a larger range. They can be quite small and quite large, but the largest of them can be up to millions of light years across and tens of trillion times the mass of the Sun. So these can be quite large. And you can see at the bottom there, I put a dwarf galaxy just to show you how big these elliptical galaxies can be in comparison to a dwarf galaxy. So dwarf galaxies themselves are actually quite common. They're probably the most common type of galaxy in the universe. They're quite hard to find because they're quite faint. Because they are made up of stars, if you have less stars and they're physically smaller, they're going to be less bright. Their luminosity is going to be low, so they're going to be quite hard to actually find anyway. But they are generally one of the most common types of galaxy that we actually have in the universe. Now, where do we normally find them? Well, quite often they're actually satellites of larger galaxies. So the Milky Way actually has satellite galaxies or dwarf galaxies orbiting around the outside of it, as do other galaxies. When we actually look out and find these bigger galaxies, we find that dwarf galaxies are quite often orbiting or interacting with larger galaxies nearby. That's quite common to find. There are cases where some of them are isolated, but a lot of them are found around larger galaxies. So the most common types of dwarf galaxy are dwarf elliptical, ones that are more spherical. Those two are kind of similar. One's just likely going to be an elongated version of the other. You've then got dwarf spiral galaxies and dwarf irregular galaxies. So these actually are fairly similar to their larger cousins. There are obviously unique differences between them, but generally, at least appearance-wise, they look similar to the larger versions they're named after. Now, there are uncommon types as well, which can be like subtypes of those. And you've got ultra compact ones. These are like really compact ones that look more like a globular cluster. Ultra faint ones, again, the clue's kind of in the name here. They're going to be ultra faint. And then you've got blue compact dwarf galaxies, which I'm going to just cover on the back end of this video here. So, blue compact dwarf galaxies. Just like other dwarf galaxies, they are small, they're quite compact, hence the name, and they're very faint like other dwarf galaxies. So again, they share quite a few features with the other dwarf galaxies. However, the main difference here is that they appear blue, hence the name. They're blue compact dwarf galaxies. And that is unlike the other galaxies, or not necessarily, because actually if you've got a dwarf irregular, they might have quite significant blue colours to them, which we'll cover in a little bit. And actually, blue compact dwarf galaxies can actually be irregular galaxies as well. Again, it explains kind of why they're blue. But most dwarf galaxies are going to be less blue than these type here. It's the kind of one defining feature about them. Now, why are they blue? Well, they contain lots of massive young blue stars. If you zoom in on them, in fact, if you can probably see, there's lots and lots of blue spots there, lots of kind of clusters of young blue stars there. Now, the key thing there that we know about stars and massive young blue stars, or just say massive blue stars in general, they don't live for very long. So if you're actually seeing them, it means they formed not that long ago. So you've got recent star formation occurring there. Now, because of that, they actually can be referred to as starburst galaxies because they have enormous rates of star formation. Because you've got an enormous amount of blue young stars and massive stars, you've got high rates of star formation. So these have like a sudden burst of star formation, and they can be referred to as starburst galaxies. And you get starburst galaxies that are larger, the much larger versions as well. So these are kind of a little bit reminiscent of those there. And zoomed in, you've got a stellar nursery. So that's where stars are forming in these kind of clouds of gas. And then when they actually become a star, they then illuminate them and you get these really nice nebulas as well. So if you've ever pointed your telescope towards the Orion Nebula in the Orion constellation, you'll see one of these sort of stellar nurseries, that luminous cloud which actually is surrounding lots of young massive blue stars. And it's the same thing here, but it's happening on a much larger scale in comparison to the galaxy that they actually reside in. Now, because of all this huge rates of star formation, you actually get an enormous amount of wind. So these galaxies can be quite windy places. It sounds bizarre. It's stellar wind. So massive stars do have significant stellar winds associated with them, and they can impact the surrounding area. They can impact the formation of stars in the same cloud. They can impact how planets form. So planets rarely, or they will struggle to form around a massive star due to these enormous stellar winds. So maybe if we're looking for habitable planets, maybe these blue compact dwarf galaxies are not going to be the best place if we've got an enormous amount of these massive stars in these kind of windy environments, because they can be quite violent locations. Now, because of all of this, or this might be a precursor as to why they're having lots of star formation occurring at the same time, is that they are irregular in shape. So they don't have a kind of uniform, symmetric shape like an elliptical galaxy or one that's more spherical, even as a spiral galaxy. They are quite irregular, so they don't all look exactly the same. And you can see in the background here, you've got a blue compact dwarf galaxy there, and it doesn't have a symmetric shape, so it would be known as irregular. And because of all that rapid star formation, it does create a violent environment, so it can impact the actual evolution and the ongoing formation and shaping of the galaxy itself. Now, a lot of those, why are they irregular? Well, a lot of them have been found to be interacting with other galaxies. So I said that a lot of dwarf galaxies are orbiting around the outside of larger galaxies. Well, as they do that, and if they get too close, they tidally interact. So the bigger galaxy will actually tidally stretch or even strip material from the smaller galaxy, and they can actually eventually merge as well. They can collide and grow in size, but all of those processes distort the underlying original shape of that galaxy, so they then become irregular. Now, that could actually drive these huge rates of star formation. And why does it do that? Well, if you've got tidally interacting galaxies, if they have gas in them, that can actually cause a collapse or gravitational instabilities in the gas, and then that collapses to form new stars. So it's kind of like a catalyst. Tidally interacting galaxies, you can then essentially start star formation, assuming they have gas in them as well. Now, this is a sample of some tidally interacting blue compact dwarf galaxies. So I've put BCD here. If you look at any academic papers, they'll kind of refer to it as like BCD type galaxies, which basically just means blue compact dwarf galaxies. And the top is the actual images of that, and on the bottom you've got the contours then of around the actual galaxies, and you can see they're kind of irregular in shape. Some of them actually do have like kind of streams of material being pulled out of them. So these are a sample of tidally interacting. So we know that a good proportion of these are interacting with other galaxies, which is most likely what's driving the rapid rate of star formation in them, because it will cause a local collapse in the gas, which forms new stars. However, they could also have formed from the merge of even smaller dwarf galaxies. So if you've got two smaller dwarf galaxies, they collide and merge. That again in itself could actually be a catalyst to star formation. You get a collapse of a significant amount of gas all at the same time. You get a sudden spike in star formation. That could be a reason, or a formation process that creates these galaxies as well. However, quite a few of these blue compact dwarf galaxies have actually been found to be highly isolated. That means they're nowhere near other galaxies, yet they still have significant star formation occurring. They haven't undergone any tidal interaction that is clear and can be observed easily. So what actually is driving their star formation? And this is something that's actively being looked at the moment, because it's not fully understood, because these are kind of outliers. Whilst we can explain a lot of them due to tidal interaction, there are ones that are not undergoing that, yet are undergoing the same process. So something interesting is happening with these, and ongoing research will hopefully identify what might be going on here. So thank you for watching, and if you enjoy the videos and you find them useful, then do consider kind of becoming a member of the channel. There's extra videos in the member section, and it also just helps support the channel in general. So thank you for watching.